Alright everyone, welcome back. We're doing part 2 of conservation of energy. We're going to be doing conceptual example number 12. There is a video to go along with this, but I can't really show it for this. Okay, so a woman drops and falls from point 1. She lands on a trampoline, point 3, and lands back to where she started at point 1. Draw an estimated bar graph showing the gravitational potential energy and kinetic energy and elastic potential at each point. Yeah, the video is pretty cool if you've ever seen people doing trampoline tricks. But anyway, here we go. So right at the beginning of point 1, drops and falls. So we're going to say, it's up to interpretation, but we're going to say like a maximum amount of potential energy because it's really high up in the air. If it's dropping, no real kinetic energy starts out with, if you made a little, I think that's okay, and no elastic potential energy. Okay, so number 2, pretty far down, about to hit the trampoline, so potential energy has definitely gone down a lot of kinetic energy, and no real elastic potential energy because nothing is stretching or bending or whatever. At point 3, a little bit different. It's hard to see exactly what's going on, but we can see that, in the middle of the bounce, depending on how much the bounce is, there's no potential energy. This is kind of like the lowest point this person is going to be. We don't know how much this person is moving, so it's kind of up to you, but I'm going to say not too much movement and almost all elastic potential energy. Okay. And number 4, on the way back up, this person is higher, so that means the potential energy should be more than 2. So I'm going to say I'll do it like this. And maybe kinetic energy similar like this. No elastic potential energy. Okay? And it should look something like that. Okay? It could look a little bit different depending on how you interpret things, but that's how it is. Alright, number 3. A ball is dropped from a height h and lands on an unstretched spring, which is then compressed as shown in the diagram. What would have happened to the spring if the ball had dropped from a higher point? The spring would compress more. B, the spring would compress less. C, the spring would compress the same amount. Well, okay, so what's essentially happening here is all the potential energy is turning into all elastic potential energy. So if the ball was higher, that means there'd be more potential energy, which would mean there would be more elastic potential energy. And how that would be more is if it compressed more. So it would be A. Moving on. A ball is dropped from a height h and lands on an unstretched spring, which is then compressed as shown in the diagram. Let's say the spring is replaced with a different spring with a higher spring constant, and the experiment is repeated. What would happen to compression of the spring? Okay, so what's going to happen is this is more stiff. Okay, so this spring is more stiff, so that means we know is elastic potential energy is equal to 1/2 kx squared. So what's happening is this this k is up because the spring constant is more stiff. But the potential energy getting converted to elastic potential energy is going to be the same. So if it's more stiff, that means it won't compress as much. The compression will go down to counterbalance. So the spring would compress less. Moving on. Look at the diagram below. At what point or points is the bowling ball experiencing potential energy, kinetic energy, and elastic potential energy? Okay, so at point A, it's not moving, so all potential energy. Point B is potential energy and kinetic energy. Maybe I won't go through all of them. But point D, we can see that it's still stretching, so it's not at the lowest point, so there's potential energy. It's moving, the ball is still going down, and it has compressed the spring a bit, so it should be D. Alright, example 16. Look at the diagram below. At what point or points is the bowling ball experiencing only potential energy and kinetic energy? Okay, so only potential energy here because velocity is 0, but over here there's going to be potential energy and kinetic energy. Over here the spring has not compressed yet, so this is also going to be potential energy and kinetic energy. And like we mentioned before, part D has potential energy, kinetic energy, and elastic potential energy, so it'll only be B and C. Okay, moving on. A marble is on a spring that has a spring constant of 200 Newton per meter. The marble has a mass of 0.008 kilograms and is compressed down onto the spring 0.05 meters and let go. How high does the marble reach from the ground? Okay, so this thing is pushed down 0.05 meters, and then it goes up like this, and we want to know what this height is. Okay, so we're doing again mechanical energy initial is equal to mechanical energy final, and like I suggest you write everything down and think about what type of energy is at the beginning and what type of energy is at the end, and then do it. This is like tedious, like I mentioned in the last video, but I see a lot of mistakes students make if they don't write everything down. Anyway, people probably aren't going to listen to me, but that's okay. So the very beginning is going to be this point here, and the highest point is going to be the final initial. Okay, so at the very beginning, it is at the lowest point, so that means the potential energy is going to be 0. At the very beginning, it's also, the marble has not moved. The spring is going to accelerate it, but it has not moved at the very beginning. So there's only elastic potential energy at the beginning. Whoops. This is equal. At the very end, there is potential energy. That's part of H. That's what we're looking for. At the very top, there is no kinetic energy, so that's 0. And it's not stretching or compressing a spring, so that's 0. So anyway, we have 1/2 K, which is 200. X squared, which is 0.05 squared, is equal to M, 0.008 G 10 times H. H is what we're looking for, so let's put that into our calculator. Okay, 0.05 squared times 100 divided by 0.008 times 10. Oh wow, this went high. So we have, oops, sorry, let me do it again. 0.05 squared times 100 divided by 0.008 divided by 10, sorry. And we get 3.125 meters. Okay. Alright, moving on. Similar question. A marble is on a spring. The marble has a mass of 0.008 kilograms and is compressed down onto the spring 0.04 meters and then let go. The marble reaches a height of 2.5 meters. What is the spring constant of the spring? So very similar question. I am going to go faster just because we did a similar question just before. So if you didn't look at the last problem, look at the last problem. But we're thinking about all the energy at the beginning versus all the energy at the end. We're putting the 0 line at the lowest point the object goes. And so this is going to be the initial. And the final is going to be the highest point here. So kind of like what I said at the beginning. At the very beginning, there's only elastic potential energy. It's at the 0 line, so no potential energy, no kinetic energy because it's not moving at the very beginning. At the highest point, it's not moving. It's momentarily 0 velocity, and it's not stretching a spring, so no elastic potential energy. There's only potential energy. Okay, so let's write this down. 1/2 K, that's what we're looking for. X, it is pressed down 0.04 squared, and it's going to be M, which is 0.008. G, which is 10, and it reaches a height of 2.5. Alright, so let's do some math and figure this out. I'm going to do 2.5 times 10 times 0.008, and then divide by 0.04 squared. And we get 250 Newton per meter. Okay. Alright, moving on. Okay, I guess we're doing similar. A marble is on a spring that has a spring constant of 200 Newton per meter. The marble has a mass of 0.008 kilograms compressed down onto the spring 0.05 meters. How fast is the marble going when the marble reaches a height of 1.5 meters? Okay, so this one's a bit tricky, so I'm going to kind of write it all out. And then we'll take it slow. So again, writing out all the energies and thinking about each one. Whew, takes a while. You know, when I was in elementary school, or when I was in school, I never wrote out all my things. So I was like pretty good at math, but I made so many mistakes because I was always rushing things. Similar to how I am nowadays, but I've definitely become more disciplined in that area. Okay, so at the very beginning, it's going to be compressed down. It's going to be like this. So it's going to be at the lowest point at the very beginning, so no potential energy. It's not going to be moving at the very beginning because the spring hasn't launched yet, so no kinetic energy. There is elastic potential energy. When it goes up, so it's going to be up here like, I don't know, 1.5 meters. So there is going to be potential energy. It's going to be moving. It's asking how fast it's going. So there is kinetic energy. It's going to be off the spring, so no elastic potential energy. So let's write it all down. 1/2 k x 0.05 squared is equal to potential energy m 0.008, gravity 10, height 1.5, and it's going to be plus 1/2 m 0.008 v squared. And we're looking for what that v is. So let's simplify a lot of things. 100 times 0.05 squared, and it's going to be 0.25 is equal to 5 times 10 times 0.008, 0.12 plus 0.004 v squared. Okay, so let's see. 0.25 minus 0.12 divided by 0.004, and we get 5.7 meters per second. Okay. Alright, moving on. A ball is compressed against a spring on top of a table. The ball is then released and starts moving toward the edge of the table and falls onto the ground. At what point does the ball have the most amount of energy? Okay, so it's going to be like compressed, then it's going to move down and go like that. A, when the ball is fully compressed against the spring. B, when the ball is released from the spring. C, right before it hits the ground. It has the same energy at every point. Okay, so the answer is D. Remember, energy is conserved. So yes, it has the most amount of elastic potential energy at point A. At B, it has the most amount, it has the most amount of potential energy and kinetic energy at B. And at C, it has the most amount of kinetic energy. So, but at every single point, it has the same amount of energy. Okay? I should say total energy, total mechanical energy. Okay, moving on. A ball is compressed against a spring on top of a table. The ball is then released and starts moving towards the edge of the table and falls onto the ground. At what point does the ball have the most amount of kinetic energy? A, when the ball is fully compressed against the spring. No, that's when it has the most amount of potential energy. B, when the ball is released from the spring. A lot of people might say this, but it's not exactly it. And C, right before it hits the ground. Yes, it's going to be C. And that's because even though right when it's released from spring, it's going to go fast, it's going to get faster as it's falling. So it's going to, that potential energy that it still has over here is going to convert to kinetic energy. So it'll have more right before it hits the ground. Okay, number 12. A 44-kilogram skateboard is moving up a ramp shown in the diagram on the right. The skateboard initially has a speed of 6.5 meters per second when it starts to go up the ramp. By the time the skateboard reaches the top of the ramp, the speed reduces to 4.1 meters per second. What is the height of the ramp? Alright, again, we're writing it all out and seeing what we know. Okay, so we're making the 0 line at the lowest point the object is in the problem, so right here. So let's write it all out. Potential energy initial plus kinetic energy initial plus elastic potential energy initial is equal to potential energy final plus kinetic energy final plus elastic potential energy final. Okay, so at the very beginning, it's at the 0 line, so no potential energy. There is kinetic energy because he's moving 6.5 meters per second. There's no springs or anything elastic here, so this is 0, and I could just say this is 0. At the end, there is a height. That's what we're looking for, so there's potential energy. And he is moving, so there is kinetic energy. Okay, so let's write this all out. 1/2 mass is 44. Velocity at the beginning is 6.5 meters per second squared. And this is going to equal the mass, which is 44, gravity, which is 10, and the height, which is what we're looking for, plus 1/2 mass, 44, and at the end has 4.1 meters per second. Okay, so let's simplify this. 6.5 squared times 44 times 0.5. And we get 929.5 is equal to 440h plus 4.1 squared times 2 369.82. Alright, let's simplify this. 929.5 minus 369.82 divided by 440. And we get 1.27 meters. Great. Alright, last one over here. This also has a video, but we'll just kind of not look at it. So we have this person who is pole vaulting. And if you guys don't know, a pole vaulting stick is very elastic. It bends a lot. Especially if you saw that video, that will become noticeable. Alright. So, number 19. From the video, explain the energy transformation from each of the points indicating the diagram starting from 1. So this is 1. For each point, draw a rough bar graph showing the gravitational potential energy, kinetic energy, and elastic potential energy. Okay, so we can see at the very beginning, there really is no energy coming from the runner. The runner is just kind of like waiting to start running. And then the runner, she starts to run. So there's a bunch of kinetic energy. And she puts her pole vault here and starts to rise up. So the pole vault is giving her elastic potential energy. She's also moving up, so there's kinetic energy. And she's also going up, so there is potential energy. At the highest point, she has most amount of potential energy. The pole vaulting stick is no longer bent, so no elastic potential energy, and she's moving a little bit. And as she falls, very little potential energy and mostly kinetic energy. That's kind of how it looks like. Very cool video. Anyway, if you see a video of the pole vaulting, highly suggest it. And you might be asking, well, what happened here? How did we have no energy and then we had energy? Why is energy conserved? How is energy conserved? Well, we're going to be actually talking about this in the next unit, which is work. So we're going to be using our calories to do work that can provide energy. But more on that next time. Thanks for watching, everyone. Bye.